Hi, my name is Rob Dawes and you're listening to the Obscast.
Sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.
Hello and welcome to the Obscast, the podcast dedicated to Sherwood Observatory, its members, visitors and all budding astronomers. My name is Joe Gathercole, and this episode I'm joined by Nigel Sparky Cunnington, our radio astronomy coordinator, and of course by our reliable regular Steve Smith, who will later be handing us all his tips and tricks for August's viewing hits. And also stay tuned for the usual upcoming member and non-member events coming up for you in August. Thanks for being here, guys.
Thank you.
Thank you for having us.
This episode we are concentrating on what I believe is one of the gateway events that leads people further into astronomy, a meteor shower, specifically the Perseids, which have already started and will continue to streak across the sky and entertain us throughout August. But first I want to offer a congratulations to Sparky, who at last month's AGM was voted as the Society's new chairman. So well done, Sparky.
Thank you, Joe.
Yeah, congratulations.
How are you finding it so far?
Fantastic and getting better.
Good. I understand it comes with a heavy workload, so thank you for being here today. We're here to talk about specifically the Perseid meteor showers, but I have been asked to get some clarification on two particular points. What is the difference between a meteor, a meteorite, and a meteoroid? And after that, what's the difference between a comet and an asteroid?
Yeah, thanks, Joe, for asking that. In fact, that's an interesting question that we get asked at our open days. So let's just do some definitions here. First of all, those bits of rock that are out there in space, orbiting the sun, they're known as meteoroids. Okay, so when they're out there, they're meteoroids. When they enter our atmosphere and burn up, that's known as a meteor or a shooting star. If they're big enough and they make it through our atmosphere and hit the ground, that's known as a meteorite. The meteoroids are generally less than 1 meter across. Anything that's greater than 1 meter across tends to be called a near-Earth asteroid. So, asteroids and comets, what's the difference? Right, we're all familiar, or I hope we are, with the asteroid belt between Mars and Jupiter. A long time ago, there was an awful lot of chunks of rock out there. And one of the things that scientists used to think, and some still do, was that was a failed planet. And they reckon that perhaps the gravitational effect of Jupiter stopped it actually forming in that part. So you get big chunks of rock and metal out there. If those asteroids are greater than about 10 kilometers in size, there is enough radiation inside them to keep them molten for quite some time. Because of that, they end up very much like our Earth, with all the heavier elements actually settling down to the centre. So your things like your irons, your nickels, your cobalts, that sort of the metal ends up at the bottom. Then you get the actual softer rock around that. Yeah. So what you end up with is basically 3 different layers. First of all, there's the outer soft rock or stone. You then get a very thin mixture of rock and metal, and they are called stony irons. And then the center becomes your iron core. Okay, so that is on the larger ones. Right. So what then happens is that another asteroid comes along and smacks into it and breaks it open. And so what you end up with was a lot of fragments of these different compositions. So you get some of these asteroids which are metallic, some of them that are known as stony ions, they've got the mixture, and then some which you get as the stone ones. Now, in being impacted, what can happen is they can get ejected into our solar system towards the sun. As they make their way through, they can come across the Earth, and they come down, if they're big enough, to land, and they are known as meteorites. And so the meteorite collectors around the world pick up these 3 different sorts, and that's basically where scientists think they've actually come from. Okay. Now,
Good.
when they come down, they're known as what's called sporadic meteors. Okay, because they can come down at any time. They're not associated with anything, and basically the actual chunks of material survive, and you can actually see these 3 different sorts. The chondrites, which tend to be the stony ones, are the far commonest ones at about 70% that you'll pick up. The iron ones around about 25% ish, and the remaining 5% of these stony ions, they're the more rarer ones that you get there. So that is your meteorites coming down, and that's where you get these different compositions from. Okay, so if we now talk about what's the difference between comets and asteroids. Asteroids are, like I've just said, a solid chunk of material, whereas the actual comets are more like a dirty snowball. Okay, so they're made up of very small particles of stuff. So if you get a comet's debris coming down, I'm trying to think of a pleasant. It's like rocking horse manure. Let's put it that way. Yeah, you would be very rare, very rare to be able to find meteorites from comets, because they tend to be made up of these smaller particles.
Okay.
So that's basically the difference and the differentiation between the ones that we actually get.
Can I ask you a quick question about that? Because it's fascinating.
Absolutely.
You mentioned comments like we call them dirty snowballs commonly. Is there any chance of those having a solid centre? Some of the bigger ones, or?
That's a good question, actually. Difficult to actually say for definite, but what we can say is that they do evaporate.
Yeah.
If they had a real solid centre, there would be some evidence, I would have thought, of remainders of them. And so far as I'm aware, though, I'm not an expert on it, I don't know of any. I don't know of any.
It's just the way your explanation was very, very good and fascinating. I just wondered if you'd got something like an asteroid to start with, it could then conglomerate into something bigger with these icy, snowbally stuff, and be at the far reaches of the solar system, masquerading as a comet. I just wondered, it's such an animal might exist, that's all.
Okay, my personal opinion would be that it's very difficult to be able to achieve. Most of the asteroids live within our solar system, whereas most of the comets have come out from the Oort cloud.
Yep.
Yeah, and so they are the remnants of the build-up of our solar system out there. So it will be difficult, as I could perceive anyway, to be able to get an asteroid that's within our solar system, to get it to go out there and to start to collect up ice and debris.
So the asteroid belt and the Oort cloud are, as you say, remnants of the way the solar system was created
Right.
and built over time.
Yes, that's right.
So that's kind of just how it is.
That's
you'd
just
be
how it is.
shocked to find an asteroid out of place.
You would. There is other places where you can find the asteroids. There's two groups called the Trojan asteroids, and they actually live. One group is running in front of the orbit of Jupiter, and the other one is running behind. They sit at what you could call the Lagrange points of Jupiter, so they always remain in those points there. And I do believe that there's been one or two collectors find asteroids from those points, but again, they're very, very rare.
Yeah, I wonder how they know specifically that they came from
those
points.
One of the ways they actually do that is by the reflectiveness of light.
Okay.
So when they point the telescopes at these objects out there, how reflective they are, they can tell that it's a type A, type B, type C asteroids. Yeah.
So when on Earth we experience a meteor shower, what's happening there that's actually causing it all to be numerous meteors all at once through specific time periods?
Yeah, that's again a good question, Joe. Okay, most by far the most meteor showers come from comets. They suspect one or two asteroids, but it's mainly comets. Okay. Now, people's actually seen pictures of comets, if not actually seen them live. They've seen them, and you'll notice that they have two trails that you can see. There's actually a third trail as well that you can't usually see. So what are these? Well, let's go back to the idea that comets are dirty snowballs. Okay, so when they're living out there in the far reaches of our solar system, they're quite dormant. They don't do a lot, basically. And as they come closer in towards the sun, the heat and the energy from the sun can actually start to warm them up. And so what you end up getting is sublimation, of the ice. Because it's a dirty snowball, because this ice is sublimating into gas, it's actually releasing particles as well. Now, the sun radiates energy at different wavelengths. The gases that get sublimated off are ionized by ultraviolet radiation. And the ultraviolet radiation, once it's ionized those, it actually forces away like a jet of plasma. It's become plasma now, away from the actual comet in the direct opposite of where the sun is. So when you see a comet with a trail coming out that's pointing directly at the sun, that is plasma. That's the gases that's been ionized by ultraviolet radiation.
Is that happening all the time, or is it just as it comes into the inner solar system?
Only as it comes into the solar system to the strong reaches of the energy from the sun. Now, you'll also see a second one, and this second trail, it actually bends a little bit away. What that is fine particles that have been released out of this dirty snowball. And what you get is the solar wind this time affecting these particles and moving them and blowing them away. But you've also got the momentum of the comet, and so what you get is a curve, because you've got those two directions. You've got the solar wind in one direction, you've got the comet moving in another direction. So what you get is this nice little curve. But also said there's a third one, and that third one are particles which are a lot bigger, not massive, like grains of sand. That's all we're talking of, and those are less effective, less affected by the solar wind. And so they tend to follow the orbit of the comet.
So they stay in its orbit.
So they stay in the orbit, you see. All the others are blown away.
That explains a lot.
And so what we end up with is this comet coming round every how many ever years, and it keeps depositing these particles in these areas. Yeah,
But
once it goes round.
Gas is blown away.
Gas is blown away. Little particles, they've gone.
They've gone, and it remains the dust.
The dust.
Brilliant.
The comet running away.
Yeah, and the comet running away. Now, depending on the orientation of the orbit, it means that our Earth can actually cross that path. And I've always actually wondered, just diverting a little bit, what would happen if the comet and us
Arrive at the same
arrive
point.
at the same point at the same time? We'd have a bit of a bang.
There's
wouldn't we?
films about it.
There
Yeah.
is, isn't there? Absolutely.
Is Bruce Willis still around?
Quite. But the thing is, you see, that the Earth then passes through, if the orientation is correct, through these smaller grains that are left behind. And it's those grains that actually produce your meteor showers. That's where it actually comes from.
And we're moving relative to the particles that's moving in orbit, in
Yes.
the comet orbit.
That's right.
So it depends what the difference is, depends how fast they come into our atmosphere.
Absolutely. Yeah. It all depends on the orientations and which direction they're actually going to be coming from.
I also understand that a periodic comet that keeps coming round and round and round lays perhaps a broader tail than just a single comet passing through.
Yes.
So we get meteors over a longer period when we're passing through. Is the Perseid meteor shower one of those?
Yeah, it is. The Perseid meteor shower is actually produced by the comet Swift-Tuttle, which comes around every 135 years or thereabouts.
Right.
Okay, so it'll keep on adding to that. But I said a little while ago that the very fine dust particles are sort of blown away in an arc, but nevertheless the solar wind can affect these particles, and they can move them over a period of time. And it's quite interesting to do the tests, the observations over a number of years to see whether you get an increase or decrease in the number of meteors are seen per shower. Because let's face it, there's been showers for millennia, but a lot of those have gone, Now, it's either that the Earth is swept them all up like a vacuum cleaner, or the solar wind has blown them away. And they reckon that the Geminids in a few years will start to disappear. Because the actual wind is actually blowing these particles away from us, out of our orbit, so we won't see them again, which will be a shame, but there you go.
It's a very, very good explanation. It just brings to mind the last time I saw Halley's Comet.
Yeah.
I think it was in the 1970s.
Yeah.
It was fascinating. It was brilliant. And I can remember seeing it coming for months as a little snowball before it actually, burst into a tail and everything. But I do understand that because of its orbit, it passes through the Earth's orbit twice.
That's correct.
And we end up with 2 meteor showers for the price of 1.
Absolutely.
So that's bonus.
Yeah.
And but it's just smashing. It's all good stuff. And
That's right.
I mean, in the past, the arrival of a comet's been a portent of good or bad, in the prehistory of astronomy. So yeah, fascinating subject.
Yeah. Those two are actually the Eta Aquariids. In May the 4th and 5th, and of course you're looking at the Orionids, which is the other one for Halley's Comet as well, and that's October. The 21st and the 22nd, the peaks at in those, so they are both, as you say, for Halley's. They're on the same plane as our Earth. So yeah.
That's a very good explanation. I enjoyed that.
Yeah.
Good.
So you mentioned the Perseids are the sand dust grain sized remnants left behind by Swift-Tuttle comet. How big is Swift-Tuttle, and does that mean that it will be round about the same time every year? You'll get the same shower from individual comets.
Yeah, that's again.
It's getting
You've got some.
smaller, Joe,
You've got
every-
some.
every time.
You've
Yeah,
got
that's
some
what I
good
was thinking.
questions here,
If it's getting blasted every time it comes round, we're going to run out of Swift-Tuttle.
Swift-Tuttle is rather large, actually. It's approximately 16 miles across,
Okay.
which is a blooming big thing. You know
Yeah.
what I mean? And so it's going to take many millennia before that will actually evaporate off, and it's coming around every what did I say, 135 years, something like that, isn't it?
Yeah.
I think,
Yeah.
it's
I think that's what you
135
said, yeah.
years. Yeah. So it's going to take quite some time for that to disappear. But yeah, it keeps laying down this track, and the Earth keeps going along and sweeping part of it up. But of course, it's relatively speaking, the Earth is not going to sweep the whole lot up, you know, because it will have spread out. You know, we could talk about entropy. You know what I mean? You know, and how that
It's
increases.
getting bombarded by particles and rays
Yeah.
and everything else.
Absolutely.
Yeah.
So yeah.
And not all comets cut through our path around the sun. Some are external to it. They've got different orbits. We never see any debris from them.
No.
So we're lucky to experience a meteor shower when we you know, our regular meteor showers, and it's normally at the same time each year, isn't it? When
Yes.
we like the this Swift-Tuttle, the Perseids, it's normally around 12th, 14th for the maximum of, you know, August each year. So we can look forward to that. And some years are good, some are bad. Sometimes we get a moon, sometimes we get bad weather. But
That's right.
I've
Absolutely.
experienced a few good ones.
yeah.
When I've seen about 40 meteors an hour.
Yeah.
And I've sat there with a piece of paper and I've just drawn where they're coming from and different strengths. And then at the end of the night, I've ended up with a lot of streaks on it.
Yeah.
Really enjoyable. So I'm looking forward to this one.
Fantastic.
So
Yeah.
Swift-Tuttle, I think, last came around in the 90s.
Yeah.
Would you get a really, really good meteor shower closer to the time when it's been around for the next year, and slowly, gradually? I don't know if there's a question we know the answer to or not, but it seems to me that you would have fresh deposits
Right.
closer to it coming round.
Yes. I would say yes, but there's a caveat here. The fact that it's 16 miles across, and these particles have probably not had enough time to start to spread out.
Okay, yeah.
So you're probably going to end up with a concentration of them.
A sweet spot.
Yeah.
Mm.
And whether
Yeah.
the Earth actually hits that or not is anyone's guess, I think.
So the entropy helps us to start.
And sometimes
off
we
with it, and
don't
it
hit
takes
that
it away
sweet
from us in the
spot.
end.
You know, we don't always hit the sweet spot because our orbit's slightly different.
Yeah.
Every time we go around the sun, it's not always quite the same. We're moved by the positions of other planets and stuff like this, so it's not always bob on. But when it is, we've heard stories in the past where there's thousands in one night on a shower. It's just raining meteors, and obviously what sweet spot they've hit on, then I can't remember, but it's recorded, isn't it? You know,
That's
some
right,
really
yeah.
good,
There's
some
been
really good
ones.
showers. And sometimes you can. I think I was disappointed last year. I don't think I saw one.
Right.
You know, but this is what happened.
Yeah.
Yeah.
Well, in terms of numbers of meteorites, how do the Perseids match up against other well-known showers such as the Lyrids, Orionids, and Geminids?
They do vary slightly, but if you actually look, and okay, so let's just backtrack a little bit on that question. How do we actually count them? Okay, how do we count them? How do we define the rate of them? And it's called the ZHR, or zenithal hourly rate. Yeah, and basically what that means is if you take the the showers of meteors coming in, and you place it at the zenith above your head on a clear night with seeing properties of about magnitude 6, okay, that then defines what the ZH R is. Okay, so that's what you would define. So we can use that to define how many meteors for each of the showers that we've got. So we're comparing like for like. That is the thing, because one of the things we haven't touched on yet is the actual radiant sources, and that will make things vary a lot. So we have to have something that's the same across the whole platform. So if we take the ZHR figures, if you look at the Perseids, you're looking at between about 50 to 75 meteors an hour, roughly speaking. The Lyrids, on the other hand, are only 18. If you look at the Orionids, you're looking at a very similar sort of figure of 50 to 75. And of course, the Geminids, which are the star attraction basically of the year, is 150. So that's something to look at. But they do vary. They do vary. They do vary on the speeds. They do vary on the colours, like, you know, Steve, you've already mentioned on that, depending upon what they're actually made up of, you know. So as they
The
burn,
speeds as well, you know, are relative, aren't they?
That's right.
To a lot of things.
Yeah. Just as a sidestep, what we have is the Earth in orbit. We have it rotating, giving us obviously day and night. At 4 o'clock in the morning, if you look up, that is the direction we are going in our orbit. So anything that's in our way, we're going to vacuum clean all that up.
And it's coming in fast.
And they'll be coming in fast, yeah? If, on the other hand, you look at 4 o'clock in the afternoon and look up, that's actually where we've come from. And so meteors have got to catch us up, yeah? Now, the problem that you get, that if the meteors are not travelling at a minimum rate, don't ask me what that is. I think it's about 20
miles
a second. Yes, I think you're right there, Steve. Yeah, it's around that sort of figure. They won't produce a trail. They won't burn up. And so you won't actually get to see them.
Okay.
Yeah. On the other hand, at 4 o'clock in the morning, brilliant time. Get out there, eyes up. You'll see lots of them coming in. You know what I mean?
And some showers have finite peaks. I think the Perseids has something like a 4-hour slot, whereas if we're facing that 4-hour slot, we're likely at night, then we're likely to see, you know, a better shower than if we miss that, but which can be about half the rate. So it could be about 20 to 30 meters an hour either side of that peak. But just think about them though, they're spread over a few weeks. So they're really spread out in space. And we're going, like Nigel said, about 20 miles a second. So think of the amount of space we're covering, and we're still hitting meteors night after night. So it is quite amazing, really.
That's right, yeah. I'm going to go slightly off piste here and just mention about the recordings that we've had from radio meteor detection here at Sherwood Observatory, and was looking at the quadrantis in January a couple of years ago, and we actually had 2 peaks. We recorded it over quite a number of days. There's something 5 or 6 days that we recorded the things for, and we actually had 2 peaks come through. So it was a bit like, I guess, if you had a tube and you entered one side of the tube, we had a peak, and then it dropped off, and then we went out the other side of the tube.
Yeah.
We hit another peak in there, which I've never seen before. That was so I got quite excited about that, actually. I must admit.
We could hear the cheering outside the radio astronomy centre. If I could ask about, we were talking about the peaks of the Perseids and looking at 4 a.m. and travelling into them. If I was going to go out during the peak, which I think is the 11th, 12th and 13th of August this year.
Ideally.
What is the optimum time to look, and how do you get the best viewing experience? Basically, which direction do I look? Is looking up good enough, or is there a general place?
Right. Okay. So what we need to start to define now is where these meteors are coming from an objective point of view. Okay. What we actually see. Meteor showers are named by the direction that they're coming from, and that is called the radiant. So if you look at a radiant, the radiant is coming 360 degrees. So you've got a point in the sky, and all the meteors seem to propagate from that point in the sky in all directions.
Okay,
not just one, but in all directions. It's interesting to note that on another experiment we did, we recorded one particular shower, and it started to increase at 6 o'clock of an evening, and we started to get this increase. And we kind of scratched his head about this and thinking, why is this happening at 6 o'clock? And we suddenly realised it was the radiant coming up above the horizon.
okay.
So before 6 o'clock, we was picking up a number of them, half of them. But as it rose, as the evening progressed, the numbers started to go up because of this radiant. And the radiant is named in the actual constellation that it's situated in. So when you've got the Perseids, it's in Perseids.
In Perseids,
or
Orionids.
It's Orionids, yes, and it's in part of that constellation that you're looking for. So to get a good view, you want the radiant quite high in the sky. You want it, which is another point about the moon. Yeah. Because if you've got a bright moon, you're not going to see it, or a lot of rain.
The glare.
The moon likes to do that, doesn't it, to us?
It does, absolutely.
The sky becomes brighter.
Yeah.
That's
and
right.
you can't see the faint ones.
That's right. So there are a number of things to actually look for when you're planning these out. One is the radiant is going to be high in the sky. You're going to be looking at the moon.
So the radiant this year on the 12th, 13th, about between 1 and 2, if you can manage that hour, or a couple of hours either side of that, and then you're in with the best chance. And the moon itself is a thin crescent, and it's out of the way, which is unusual.
Yeah, I think it's about 10%, isn't it? A waxing crescent.
Yeah, so I mean, last year and the year before, the moon was a problem.
So now all we need is for the clouds to behave. And
Absolutely.
We could have the perfect Perseids.
That's the other thing.
Yeah.
The British weather.
Yeah. Quite. But not for radio detection.
Not for radio.
And we'll get onto that in a little while.
My next question, actually, is how do you go about detecting meteors travelling so fast through our atmosphere using equipment on site here at Sherwood Observatory?
Right. Okay. We're going to go back in time, because we need to tell a little bit, or I feel we need to tell a little bit of the story about that. And it concerns a guy called Bernard Lovell. You might have heard of Bernard Lovell. Bernard.
That is the end of part 1 of our Perseids and radio astronomy special with our radio astronomy coordinator, Sparky. Part 2 will be available in a few short days. Thank you for listening to the Obscast.